Fresh air is good, it's healthy.
I have to leave right away.
Okay, today we are happy to have Xoán López from Santiago de Compostela. Xoán is working on, he's a PhD candidate in the University of Santiago de Compostela and working with Professor Carlos Salgado. Yeah, and Andrew. And he's working in theory of geophysics in hydrodynamic equations. He mainly focus on developing the existing jet quenching formula to including the effect of hydrodynamic evolutions. And recently he studied the color decoherence effect of the QCD cascade in the presence of matter. And now he will focus on he will extend the formula to the proton nuclear collision and HIC, and also for the LC, and his application for both LC and HIC. And today he will give us the imprints of the medium evolution in jet quenching. Okay, please.
Yeah, so thank you very much for the introduction and for you to be here. And yes, I'm going to talk about the imprints of the medium evolution in jet quenching. And this is based in these 3 papers that I have been doing while doing my PhD in Santiago, under the guidance of Carlos Salgado and Andrei Sadoviev, and in collaboration in different combinations with these other people, Zhao Barata, Matvey Kuzmin, and Jared Creighton. So let me start from the very beginning. We want to study QGP, so what we do is we collide heavy ions at 2 relativistic energies. And in these collisions, we create states that are very excited and very far from the equilibrium, but they rapidly thermalize and suffer a hydro-like expansion, cooling down until they are hydronized and reach our detectors. This happens extremely fast, and basically we have two sources of information. One are the soft particles that come directly from the bulk of this thermal matter, and the other one are hard particles that are created on the ion-ion collisions. In particular, in these ion-ion collisions, you can produce very energetic partons that travel through the medium, suffering a QCD cascade, and then they hadronize as jets, and they appear in our detector. While these highly energetic particles are traveling through the thermal matter, they interact with it. Due to these interactions, the matter gets modified, and looking at the modifications of the matter, you can learn about the properties of the medium. On the other side of the same story, while the jet is going through the matter, the jet itself gets modified. And the thing is that looking at the modifications of the jet, you can learn about the properties of the matter. This is the basic idea behind the concept of jet tomography, where the main goal is to be able to use jets as differential probes of the spatiotemporal structure of the thermal matter that is created in these heavy ion collisions. And here in this talk today, I want to address a very simple question, and is whether jets are able to fill transverse flow and transverse anisotropies of the quark gluon plasma, as this water jet here in Geneva Lake is filling the transverse anisotropies and flow of the air that we usually call wind. So in order to do that, we should know that there are 2 leading perturbative processes that can modify our jets. These are the transverse momentum broadening and the medium-induced gluon radiation. The transverse momentum broadening is the fact that if you have a high energetic parton going through a medium, it will interact with it and it will receive slight kicks that will make their transverse momentum to broaden. On the other hand, these slight kicks can induce your parton to radiate extra gluons that would not radiate on the vacuum, and this is the medium-induced gluon radiation. In order to make a theoretical formulation of all of this, which is usually called in the literature jet quenching, one needs to take several assumptions to make it tractable. But we should be very careful, because if these assumptions are too strong, then we theoretically decouple our jets from the medium, and then we can no longer we no longer have theoretical control on how the medium is affecting our jet. So here I want to show you how to relax and what the implications of relaxing these approximations are. In particular, I will focus on relaxing the approximation of static and homogeneous matter on the transverse plane, which is very common. So we want to study the scattering of a particle with a medium. This is a very tough problem in quantum field theory. So what we are going to do is to substitute the effect of the medium by a classical color stochastic field that is generated by some heavy sources. First, we can assume that these heavy sources are static, and we can solve for the field, and we get something like this, where you see that the field has only one component, the zeros, which is natural because the sources are static. And then you see that we need to sum over I, where I is the level of each source. We have this Fourier factor where Q is the exchange for momentum with the medium, xi the position of the source I, then the color projection, the projection of the color of the source into the generators of the algebra, and this object here that is the model-dependent scattering potential that controls the jet-matter interaction. But now we can move from this picture and allow our sources to move with some for velocity u mu. And this means that our field now no longer has just one component, but it's going to get aligned with the for velocity. And now the delta function that was ensuring not energy transfer with the medium also changes.
So why should this always be aligned with the for velocity, the field?
Yeah, so this is what you get when you solve for moving sources.
All right, I'll take your word for it.
Yeah, you solve the like Young-Mill-like equations, and you see that they look like u mu.
Okay.
Now for this model-dependent scattering potential, here I'm showing the Ulassi one scattering potential. There are many on the market. In particular, almost everything that I do is independent of which model you want to plug there. But then, for example, in order to create the actual plots that I'm going to show you, we have to choose something, and I'm using this one. So we are dealing with a stochastic field. This means that we need to specify what the correlators of this field are. To do so, we are going to keep it simple, and we are going to assume Gaussian statistics. This means that only pairwise correlators of the field are going to be non-zero. Furthermore, when doing this, we are going to enforce color neutrality, and this basically means that we are going to require that the scattering source that we interact with in amplitude and conjugated amplitude is the same. And then we are also going to require that there is no color transfer into the different parts of the medium.
So I have a question about this Gaussian statistics. I guess the flow of the medium is in the U, right?
Yeah.
So the Gaussian statistics, I guess, is just that you have a flat thermal distribution plus the flow.
No, the Gaussian statistics means that you are dealing with this stochastic field, and you need to specify the correlators, and then these correlators will tell you,
But I mean, does the Gaussian statistics tell you that it's not correlated?
No, Gaussian statistics tells you that the field behaves like white noise. Basically.
Yeah, okay, so there's no correlation.
Yeah.
But of course, flow causes a correlation. But I guess you don't worry about that because that gets stuffed into you.
Yeah, exactly. They are like different correlations. They do not necessarily mean the same here.
Yes.
Yeah. And then we're going to perform this source averaging, which means that we're going to substitute the discrete sum over the sources by an integral over the whole space with some number density of scattering sources. When computing our diagrams, we have some hydrodynamical variables. We can call in general G, and this G will depend on the longitudinal position set. And here I should make a disclaimer. Whenever I talk about longitudinal position, this is longitudinal with respect to the direction of the jet. So Z is along the direction of the jet. But these hydrodynamical variables can also depend on the position on the transverse plane, here, X. In particular, in the model that I'm presenting here, we have 6 hydrodynamical variables: the number density of scattering sources, the screening mass of the potential, and the 3 components of the velocity. When people compute this kind of thing, so the diagrams, they usually assume that the medium is transversely homogeneous. So then you drop this dependence on X. And this means that when you are integrating over the position on the transverse plane, this just gives you a delta function. that ensures that the exchange transverse momentum with the medium is the same in amplitude and conjugated amplitude. But here we are not going to do that. We are going to assume that the function does depend on x, the hydrodynamical variables do depend on x, but they do it slowly, so we can expand in gradients and truncate the series after the first order. So then we keep this term here, and this term gives you this correction where we see that the small gradient couples with the derivative of the delta function. Then when computing our stuff, we just have to integrate by parts, and it will hit the rest of the line. So we already know how the flow and the gradients enter this whole business. Now we can start doing cool stuff. And the first thing that we can try to study is matter that is homogeneous and flowing. So we assume that the matter has some flow on the transverse plane, but there are no anisotropies at the moment. And we want to study a very high energetic particle that is going along the z direction, and suddenly it radiates a soft gluon. And we want to study how the presence of this medium flow in the transverse directions are going to affect this spectrum of the gluon. We're going to do this in the dilute regime. This means first order in opacity. Basically, we are just considering one scattering at the level of the amplitude with the matter. So, to get the medium-induced radiation, we have to compute all these diagrams. These are called the single Born diagrams. Basically, you just have one interaction with the field at the amplitude level and another one in the conjugated amplitude level. And then you have these double Born diagrams that are like virtual corrections when you have two interactions in amplitude or conjugated amplitude. I'm not going to enter in details on how to compute these diagrams or technicalities or whatever, but let me just mention two assumptions that we are going to take. First, in this business, we are always assuming that these partons are very energetic, and then we perform what is called the aconal expansion. And this means expansion on inverse powers of this energy. Here, we are going to keep the first corrections to the leading order. And then we're going to assume that the medium is dilute and extended enough, so we can neglect the model-dependent poles that are coming from this model-dependent scattering potential. So doing so, we get the amplitude square, and with the amplitude square, we can build the final state parton distribution. This final state parton distribution depends on x, which is the energy fraction of the gluon, on k perp, which is the final transverse moment of the gluon, and in E and P, which are the energy and transverse momenta of the initial quark. We're going to assume that the gluon is soft compared to the initial quark, so x is small. And under this approximation, we can see that the final state parton distribution can actually be factorized into some initial parton distribution that accounts for the creation of our energetic quark and only depends on the kinematics of this initial quark. And then this object that is called medium-induced soft gluon spectrum and only depends on the kinematics of the gluon. This is the object that we want to study. I'm not going to show you the analytical results for this object because they're pretty extensive and it's not very illustrative, but we can look at the plot of it. Just a technical detail, this plot, in order to make these plots, I took one extra assumption, and is that the number density of scattering centers is smooth on the longitudinal direction, so I can take the longitudinal interval analytically. Here I'm showing you the medium-induced spectrum multiplied by k perp squared, so the final transverse moment of the emitted gluon squared, for two different energies of the emitting gluon. And then for each energy, I'm showing you two different lengths of the medium. What we are seeing here is that when the final transverse momenta of the emitted gluon gets aligned, so parallel with the flow, an angle of 0, here you don't see very well, but it's the dot dashed line, then we see that the spectrum gets enhanced. While when the final transverse momentum of the emitted gluon gets anti-parallel to the flow, that means an angle of pi, the spectrum gets depleted. So what we are seeing here is that the medium-induced spectrum gets anisotropic on the transverse plane, and now we have a preferred direction for our emissions, which is the direction of the transverse flow. I have also to mention that this directional effect is suppressed by 1 power of the energy. So the larger the energy of the emitted gluon, the smaller this effect is. So we are already in position to answer at least partially the first question that I raised in this talk, and it's yes, jets can fill at least the flow on the transverse directions. Now we can move and try to study again the medium-induced radiation, but now in an isotropic but static matter. This means that we have a highly energetic pattern going along the z direction, and suddenly it radiates a soft gluon, and we want to study how the presence of the gradients of our hydrodynamical variables will affect this spectrum. Now, this calculation that I'm going to explain here is done in the dense regime. This means that this is the relevant diagram that we have to compute, where the particles can interact a number of times with the background field, and actually we have to resum this number from 0 to infinity. By doing so, one can see that this diagram can be written in this very nice form, where we can identify J, which is the initial source that produces our pattern, then these two W's, that are Wilson lines, the effective propagator of these two very energetic quarks, and then this G, which is the two-dimensional effective propagator of the gluon. This is basically a propagator a quantum mechanical propagator in 2 dimensions, where here you have this matrix potential that comes in a Wilson line that takes into account the color rotations due to the scatterings with the background field.
So this is still in the Eichner approximation?
Yeah, so there are many things that are called Eichner approximation. So here we get just W's because the phases are not kept. This means that when you have in the phase something that is 1 over E, you neglect it, but the gluon is soft. So when in the phases you get 1 over the energy of the gluon, you do keep. That's why the gluon does have a full propagator. We are in this regime.
Okay.
Yeah, many people call different things aconal. So, and in for example, in small x, the word aconal also have different meanings, so it can be confusing. Yeah. Yeah, here this means that we are keeping the phases here, but here they have been neglected, and that's why we only have Wilson lines. Now we want the final Parthenon state distribution, and this means that we need to square and average our amplitude. To do so, we can use that our medium averages, the averages that I presented before, are very simple, and they are local on the Z component. So then we can split our squared amplitude into different regions. And then we have a first region that goes from where the first splitting happens to where the second splitting happens. This is usually called the formation region. And this distance is usually called the formation time. And then you have a second region that starts from where the gluon is completely formed, both in amplitude and convoluted amplitude. From the first region, you get this correlator that is called in the literature radiative kernel. And from the second region, you just get the 2-point function of the propagator of the gluon. And this basically tells us that we are accounting for the broadening of this created gluon. This 2-point function leading ordering gradients was computed by my collaborators in a previous work where they were just studying the broadening in the presence of these gradients. Now, this radiative kernel can be obtained at first order by expanding the path integral around the solution in the homogeneous case. So this way, we can write the final state Parthenon distribution. And once again, since we are assuming that our gluon is soft, so now omega, which is the energy of the gluon related with the x before, which was the energy fraction, is small compared to E, which is the energy of the initial quark, we can factorize this final state Parthenon distribution into some initial distribution that only depends on the kinematics of the quark. Here you can see that the P is missing. This is because we have already integrated over it. And then we have the medium-induced spectrum that only depends on the kinematics of the gluon. Now again, I'm not going to show the analytical form of this guy, but we can plot it. And if we plot it, it looks like this. Here, just a small note, I'm not plotting the medium-induced spectrum multiplied by k squared, but just the medium-induced spectrum. And I'm doing so for 2 different strengths of the gradients. This is the dimensionless strength. So if you want to think, for example, of gradients of temperature, this would be the gradient of temperature over the temperature squared, for example. And then for each strength, I'm plotting 3 different energies. And what we're seeing here is that when the final transverse moment of the emitted gluon is anti-parallel with the gradients, the spectrum gets enhanced. And when it's parallel, so angle of 0, the spectrum gets depleted. So the effect of the inhomogeneities is to produce an anisotropic medium-induced spectrum in the transverse plane, which has a preferred direction of emission, which is the direction of these gradients. Again, this is a directional effect which is suppressed by 1 power of the energy of the emitted gluon. So the higher the energy of the emitted gluon, the lower this effect is.
But this is still static medium.
Huh?
This is still static medium.
Now this is static, but with anisotropies, with gradients. Yeah. First, I studied the flow medium but being homogeneous. Then I studied the anisotropic medium but being static. And now, now I'm going to study a medium that is both anisotropic and flowing at the same time. We are going to start here by.
Can you go back? So let me see. So what is going in which direction? So I have my gradient there, gamma gradient of the metal.
Yeah.
So which is the quark is flowing along the gradient, or the gluon is going along the gradient, or what's going along the gradient? Or you have angle theta there, pi and 0.
Yeah. It's the radiated gluon.
The radiated gluon.
Yeah. The radiated gluon will have some transverse moment.
Yes.
And then we want to study what happens to this spectrum when we look at different angles that you can radiate this gluon. And in the case of no anisotropies or no flow, you would see that the spectrum is completely independent of the direction of K pair. It only depends on the modulus. But here, since we have gradients or flow before, you do see some dependence on the angle on the direction that you are radiating.
I understand. So if I go against the wind, against the gradient, then I get more radiation. Is that the way I should look at this?
Yes. Yes.
So I go uphill.
Yes.
Uphill I get more, and downhill I get less. I mean, so if I go from dense to dilute, I get less, and if I go from dilute to dense, I get more. Is that your gradient?
No.
Yes. What is your gradient?
Yeah. You're right. Yeah.
So if I go from dense to dilute, I get less. Or
you
more.
get more, because the gradient is from less to more dilute. Sorry, from less matter to more matter. That's the gradient.
Okay.
And you get more radiation when you go opposite to the gradient. So when you emit from more matter to less matter.
Okay.
Why?
That's a good question. Exactly.
Why is that?
I would have just thought the opposite.
Well,
Yeah, me too.
this is.
If I run into a wall, I make much more damage than if I run out of the wall.
What?
If I run into a wall, I have a large gradient. I make a lot of damage and I break apart.
Yeah.
When I run out, there's not much happening. That's why I thought
No. But you should not think of. So the one that is radiating is the quark.
And that's
It's more when it's in dilute matter.
Yeah.
Which would be not colliding into a wall.
Yeah.
I'm saying that when the quark is in wherever state
goes
of
parallel
matter
to the
it
wall,
is,
right?
the radiation, so the pieces that are spread, go preferably to the place where the wall is not there, which is not the same.
That made me sense.
Which is not the same.
Yeah.
I'm not saying that
I think I
you
get
understand what I get?
Yeah. I get
So the
it.
quark is always on the same plane, but
Yeah.
now on the same place. But now you can radiate the gluon towards the more dense part, for example, if we talk about gradients of density, or the less dense. And we see that it prefers to radiate towards the less dense.
Okay.
But
now-
if the quark moves here,
Yeah.
then I'm not saying that the radiation is bigger.
Got it.
That's a different thing.
Yeah. I think that's thanks.
And is that a phase-space effect or something?
I'm not sure what do you mean by phase space effect.
Well, what am I thinking? I'm thinking that you have a higher probability to radiate where you don't have some matter already. But I don't know. I think that's what you just said, so I haven't said
Exactly.
anything new.
Yeah. Yeah, but I don't know if I would call it a phase space effect because these particles are very energetic and in principle, at least in the jet quantum formalism, they are kind of decoupled from the
so they
matter
don't
in
care.
that sense. The matter for us is just some background field.
So then why does it care at all about the density of the medium?
Well, because it can feel the properties of the medium, right? When you compute this type of things, you have a notion about density, about flow.
So these are immediate propagators of the gluon. So the
Yes.
gluon is not just a free gluon flowing
No,
somewhere.
of
It
course.
knows about the medium.
It's stressed, yeah, it's stressed by the interactions of the medium, of course. And due to these interactions, you get some knowledge about the properties of the medium. So then I think it makes sense that if the matter has some structure on the transverse plane, then your particles will know about that.
Yeah. The only question is whether I still have to work on my intuition why it goes this way, not the other way. But at least I know now what you are doing.
Okay.
Yeah.
Yeah, sorry if I didn't
No,
make
that's
it,
okay.
clear
No,
enough.
that's fine. That's fine. Very good.
Yeah, so now we can move and study the case where we have at the same time matter that is anisotropic on the transverse plane and also flow. And we're going to do this in the dilute regime. So again, just first order in opacity, one scattering with the matter in the amplitude level. We're going to first start with the broadening. For the broadening, we just have one particle, we don't have radiation, and these are basically the two diagrams that we have to compute. Again, I'm not going to enter into details, but we are taking the same assumptions as before, basically. And with the amplitude squared of those diagrams, we can build this final particle state distribution. In order to extract physical information of this particle state distribution, we can look at moments of it. It's very useful. And in particular, we want to study this type of moments where we are going to integrate the distribution with some number of transverse momenta of the particle, and then we're going to normalize it by the integral of the initial distribution that produces our particle. For this initial distribution, we're picking here a Gaussian distribution. But if you are more familiar or you prefer to think of a delta function distribution, then in the equations that I'm going to show you, you just have to take the limit of this W going to 0. It's very simple to take. So we can first start looking at the leading even moments of this distribution. This is the average of P and the average of P cube. These even moments of the distribution, in the case where you don't have flow or gradients, are 0. But now we see that they are not 0, and they get aligned with the flow and with the gradients. This means that our particles are bending. And this bending, this directional effect, is some effect that comes with 1 over the energy of the particle. So again, this directional effect is suppressed by 1 part of the energy. But we are getting here this multiplicative correction that depends on gradients and flow, which is not suppressed on the energy. Let me focus in 1 second on that. So again, we can see the jets do feel both anisotropies and flow. And what we are seeing is that at the level of the broadening, the particles bend along these directions. These results are...
What are the particles? The particles are now the jet or the
Jet
gluons?
fragments, right?
Yeah, the jet particles.
So I have a hard part on the dense fragment. Wait, I'm still. So what is your wavy line in this diagram? Okay.
Yeah. So I have this is just broadening. So there is no radiation. I have one particle,
Okay.
and I want to study what happens to him when he interacts with the medium while traveling.
Okay. So no radiation,
And
just one particle.
Yeah, and I'm studying what happens to that one particle.
Got it.
In specific, with the distribution of the transverse momentum.
Mm-hmm.
Instead of one particle, you have to think like an ensemble of particles.
Yeah.
And then for studying that, my ensemble has some Gaussian distribution of P paired, and then I see what would be the P average.
Okay.
If you don't have these directional effects, then this is 0.
Yeah, got it.
But now you see that it's not, and it has some average, and it's because your ensemble it's bending in this direction.
Okay, yeah.
And is that because of multiple scattering with what's in the ensemble, with essentially the field?
Yeah, it's because of the scatterings with the field, but not multiple scatterings, because here I'm just considering one scattering. So even at one scattering, you see this. If you compute this in the VDMPS approach, so dense regime with multiple scatterings, you will see something like this. Yeah, you also get something like this. And this is what I was saying, that these results are in agreement with what my collaborators got also for the dense regime, but just studying flow or gradients in this problem. Now we can also study
Sorry, your gradient and the flow are now parallel, right?
The gradient and the flow are free. For me, right now, are some vector on the transverse plane, and I have never specified the direction. Then, of course, if you really want to make some, like, I don't know, plug this into some code, and the code has some hydro, and you want to couple to hydro, then the gradients and the flow are going to be related. But for me, as of now, the direction of this vector G that has the gradients inside, this is just a compact way of writing all the gradients, and the direction of this U is not fixed.
So if the flow and the gradient are opposite directions, what do I get?
If they are opposite.
Yes, I mean, I'm not saying this is realistic, but we are doing theoretical physics, so we can dream of everything, right? So would that they should intuitively, I would think they compensate each other, wouldn't they?
The directional effect.
Yes.
Well, if they are such that the power of this term and the power of this term become the same, yes. But that will also depend on the strength of the gradients and the flow. But they can compensate each other, of course. Okay. In this effect, yes.
Yes.
Yeah, in the directional one.
Yes.
So, and these were, sorry, I said it wrong. These are the odd moments, not the even ones. Now we are going to study the even ones. And in particular, I want to focus on the quadratic moment. And when you study the quadratic moment of the distribution, you get this thing here, where this is just the vacuum, basically, the width of your Gaussian distribution, and then you get this through the interaction within it. And why I want to study this one is because if now we differentiate over the length of the medium, we get the p per squared per unit length. And this is exactly the jet quenching transport coefficient, what in the literature is usually called Q hat. And what we see is that Q hat has this multiplicative correction that we were seeing before, and this term here. And if you are familiar with it, I'm not sure, this thing is just what you would get if you compute Q hat in the anisotropic and static case. So basically we have that Q hat now is the isotropic Q hat, let's call it, multiplied by this correction. But now this correction is very interesting. This correction comes as a product of the gradients and flow on the transverse plane. So you cannot have this type of correction separately. It comes intrinsically from the interplay of both. And then you can see that it's not suppressed by any power of the energy. So this is leading order. And then you can also see that these have some set here, and set is coming from the length of the medium. So when you integrate over the whole length of the medium, this is going to be enhanced by 1 power of the length. So we expect this to be very large. And now you may wonder,
again, so G times U. So it seems to me, I would have thought intuitively, I don't care for the broadening of this, whether the gradients and the flow are parallel or interparallel, but apparently it does matter, right?
It does matter, Okay. Actually, you can see if they are orthogonal, then this does not exist, and the even moments do not get modifications. You still would have the directional effects.
So these are 3 vectors or 4 vectors you have?
These are 2 vectors. These are just in the transverse plane.
Okay. So, I see. Okay, so if they are orthogonal, then I have...
Orthogonal on the transverse plane.
Yes.
Why we only care about the transverse vectors? Because the longitudinal direction...
Yeah. But it's not a 4 vector. Don't have 0 components which mess up the intuition, right? So indeed, if they are orthogonal, they have no effect.
Exactly. You don't have this interplay.
And that just means that you get the static medium Q hat.
This means that the Q hat for this medium and static and anisotropic medium would be the same, even though you still have the directional effects, disturbing the substructure or whatever.
So the amount of energy loss is no different, but you get some bending.
Exactly. Yeah.
That is counterintuitive.
Yeah, because I just thought now you have all these gradients, you get more stuff in there for always problems, but apparently not.
Well, but that's only a very, very special case when you're 90
Yeah.
degrees, right? Most of the time it's.
Yeah, but I
not
can
valid.
even change the sign, right, of this term.
Yes, you can.
I can reduce it and I can enhance it.
Yeah.
It's up to you. See,
But
I
this-
mean, that's
but this-
isn't that nice?
But this is also what we were seeing for the directional effect, right? The medium-induced spectrum was getting depleted or enhanced.
That's true.
Yeah, but in this
Basically
case,
the
it's
same.
much easier to see because I have a very simple formula, right? I mean, there I can actually run it down or run it up, right?
Yeah. Yeah, yeah.
This is funny. Okay, very good.
But in principle, you're not allowed to select for the flow or the gradients wherever you want.
Okay. Yeah, if,
You are in nature
Barbara
and then
has,
you have
Barbara
to-
has this problem. I don't have to.
That's true.
Yeah. So as a mental experiment, yes.
Yeah, exactly.
As a real experiment,
Exactly.
no.
Yeah, right, exactly.
Generally, for example, in hydrodynamic conditions, large system had a smaller Q head compared to a small system. The small system had larger flow velocity and a larger gradient, so this term should be larger in small system compared to large system. Then at same temperature, the small system should have a smaller effective Q head compared to large system.
But the Q hat for a small system is pretty small, so
Yeah.
maybe it doesn't matter.
So
But you have same QEP medium. Okay, yeah, the L is
Yeah, but C is tiny.
okay, yeah,
yeah.
okay. Mhm.
So what was the question again? Sorry.
I mean, this term compare seems small system, large system have different value, different number.
Yeah, of course. So this value for small and large system is going to be different. For large system, this value is much larger.
Right.
And then the gradients and the flow that you are going to have, if you have any flow in small systems that maybe you have, then the value are also going to be different, especially the gradients, I guess.
Yeah.
So yeah.
Yeah, but C gets small. in
Yeah,
size.
T is also smaller because it's 1/4 of the length of the medium, so everything gets much more small.
Okay, yeah, it's complicated.
Yeah.
Can I have UZ to be 1 in the denominator?
No.
What is UZ? That's
So UC is the longitudinal component
of the flow.
of the flow.
Oh.
So if UC was 1, it looks like this, something would happen, but then U would be 0 from the beginning. So you would not be able to do all this.
Okay, okay, fair enough. Good. All right.
Should I move on?
Yeah.
Okay. So I'm telling you that this thing can be large, and we want to make a rough estimation on how large this thing can be. And in order to do so, first we're going to assume that we only have gradients of temperature and within log, keep it simple. And then we're going to say that everything is independent set. So here I can integrate both sides from 0 to L. And then we have Q hat L, and then this thing here. And we are going to assume also, since we only have gradients of temperature and within log, we only have gradients of rho because the gradient of mu come in the log. Well, whatever, this G that were before the compact way of writing all the gradients, in this simplification, we just get gradient of rho over rho. And now, in order to evaluate this, we're going to assume that rho is roughly T cubed. So then we can rewrite this as this thing here. And we see that the effect depends on the length of the medium, the dimensionless strength of the gradients. This is what before I was calling gamma T. The temperature, the transverse, the absolute value of the transverse component of the flow, and then the angle between the gradients and the flow. And here I just pick some sensible parameters to get some numbers, and then I can plot the ratio. So exactly, I'm plotting this modification, the ratio of the nu Q hat with respect to the isotropic Q hat with respect to the angle. So when both are parallel, we see that the effect makes the nu Q hat to be as 1/2 of the old one. And when they are anti-parallel, it can go to something like 3/2. Indeed, when they are orthogonal, you just get 1. Yeah. And here I should make a small disclaimer. This
For the EIC, that means there are no flow velocity, so just a constant one.
Maybe there's no flow.
So yes, in the nuclear reactor frame.
Well,
Yeah,
we
so-
got there with no flow and
So if there is something that you can relate to the flow in EIC, then you would get this effect too. If there is no analog, then no. Yes.
Just constant one.
Yes. It would be like the Q hat for a non-flowing medium.
Okay.
Yeah. Yeah, and I should make a disclaimer, these values here should not be interpreted as any sort of prediction or anything like that, because we are actually taking a rough approximation. We are assuming that rho is just the cube, we are just taking logarithms of temperature. This is a rough approximation. But we can also make this rough approximation for the directional effects. And we see that a particle of 50 GeVs would bend around 1 degree, more or less, and a particle of 20 GeVs would deflect around some degrees. And now we have already understood the momentum broadening, we can study the other effect, the medium-induced radiation. And in this case, what we have is a highly energetic particle, a quark, that is going through a medium and it radiates a soft gluon. And we want to study how the presence of both now, these anisotropies, these gradients, and this flow on the transverse plane will affect the spectrum of this gluon. We're going to do this calculation again in the dilute regime, so no resummation, just one scattering with the medium. And here I need to convey a very important message. We already know that the directional effects are going to be there, because we already saw them in the homogeneous and in the anisotropic case and in the flowing case separately. But what we want to focus now is in this leading order correction that we were seeing, to see if we can also obtain it here. In order to do so, we have to compute these diagrams that are the same as before. We take the same assumptions, and we build the final state Parton distribution, which again depends on x, k, p, and e. You already know these variables. We assume that the gluon is very soft, so x is small, and then we can factorize it into the initial distribution and the medium-induced soft gluon radiation. And we want to study this object. I'm not going to show it analytically because it's very ugly, but we're going to plot it. Here I'm doing the very same trick in order to integrate over the longitudinal position, and then, on the longitudinal coordinate, and I'm plotting the medium-induced spectrum multiplied again by k per square. I'm doing this for two different energies of the emitted gluon and for two different lengths of the medium for each energy. And here this is very important. What we are seeing here is not that the spectrum gets anisotropic. What we are seeing here does not depend on the direction of the final transverse momentum of the emitted gluon. What we are seeing here is an enhancement or depletion of the spectrum, a huge one indeed, which depends on the alignment of the gradients and the flow, as we saw exactly for Q hat. So again, here we can get the multiplicative correction that looks exactly the same. So this means that we have a leading order correction to the medium-induced spectrum. And this is crucial because the medium-induced spectrum is the object that controls the energy loss of the jet.
So can we can we measure this by looking at the energy flow in the jet in medium?
The
Energy flow within the jet, inside the jet.
Probably, yes. Yes. So it's very difficult to answer that question right away, because in order to plot here, I also assume that the gradients are like gradients of temperature, that things are independent of Z and whatever. So what one really needs to do is to take the actual formulas that we have in the paper and then take a realistic simulation, and then you plug the real gradients and flow and you see how it comes. So it's difficult to tell you like, yeah, you can just go and measure, but in principle, yes.
Well, the question was more how you would measure it.
Yeah, that's the difficult thing.
I mean, these days I like energy correlators because they do measure the flow inside the jet. So you're laughing because of course I would ask that question.
Actually, I'm doing a visit in UCLA to Sean Bocan's group, and we are studying energy correlators there and the modifications in PA and EA. And eventually we want to plug these effects there and see what happens.
Good. Be sure to tell us. We're about to publish the data in the next 6 months.
Yes. We are working on that data actually. Yeah, but
The person who did the analysis is connected listening to your talk. Anjali.
okay. Yeah. I know the name from that. Yeah. Hi.
Sorry for the distraction.
Yeah. So I cannot tell you right away how it will look, for example, in EEC, but hopefully I will be able to tell you in a couple of months.
So what do I make of a negative value of the spectrum?
Yeah, so this negative value of the spectrum, if you integrate over K pair, it never becomes negative. And basically what it's telling you here is that you get a suppression with respect to vacuum. Because this medium-induced spectrum, you have already subtracted the vacuum spectrum.
Okay.
This is something
Barbara doesn't measure negative jets.
Yeah, no, of course not.
Well, I'm not supposed to.
But this is just telling you that.
Right. Oh, yeah, I got it. Okay.
Yeah.
It's a difference.
Yeah.
That's fine.
Yeah, because of course you have like the full spectrum, but then you actually want to study the medium-induced part. So you subtract the vacuum. Yeah. I don't know where I was. So yeah, I think I already said this, but this object, the medium-induced spectrum, is the one that controls the energy loss. And this would be very important for energy loss. And actually, I'm doing some preliminary inspection because this effect could be key to understand things like the RAA-V2 problem. Because this tells you that the energy loss can get modified depending on where you are going in matter, because gradients and flow are going to be different. This could be important. So just to finish, yes, we answered the question in the beginning. Jets fill everything, and we should take this into account. And here I have the summary. Jets fill the transverse flow and anisotropies. They get bended, substructure gets distorted, the energy loss gets modified. The next step is to take this theoretical formalism, and this is ready to plug into actual simulations, real simulations of heavy ion collisions to see how observables look and what we can measure. And we should take this into account, and actually this brings us close to probe these effects in experiment and actually achieve actual jet tomography. And this is everything. Thank you.
Very good.
Perhaps time for question.
So in real life, isn't the gradient and the flow always parallel? Because we have a big gradient, I get hydroflow. So I'm just trying to see, I'm thinking about how I could engineer the opposite, but I see that it's probably difficult.
Yeah, I'm not very familiar with that, but I guess it's not always the case, right? You can have some gradients, not necessarily the flows going in that direction.
Then where do the gradients come from?
So, so for example, you could have, for example, hot spots in your medium, and then that gives you some gradient of temperature, but then the matter is flowing somewhere else, for example.
These are then small, then I get it, in your formula I get a small count for that, right? I mean, the big stuff is...
Right, the hot spots are the tiny spots.
Exactly.
Yeah, but the L is along the medium. So if going along the medium you find just one hot spot and then you go, probably it's small. But then if you find several hot spots, then it doesn't have to be that small. Actually, in a hot spot, the gradient can be pretty large.
Right.
Yes.
And don't we expect to have little hot spots due to where the partons are inside your colliding nucleons?
We do expect to have hot spots. But that's why I'm telling you. So the behavior of this stuff is pretty intricate. So it's very difficult to make predictions over the top of your head. You should take some simulation and actually see what happens. Because it's true that they could add up, they could cancel, they could do many different things. So yeah, I'm sorry, but I don't have that strong intuition to actually tell you what would happen in the middle. This is the theoretical formalism. Now we have to plug this in actual simulation.
So what is it? What was it again? The Q head gets larger or smaller if the gradient and the flow are parallel.
So if the gradient and the flow are parallel, the Q hat gets smaller.
More.
Yeah, because of this
Yeah.
line. So this minus this is very interesting, right? Because when first we saw this, we thought, oh, this can be large. Fuck, what happens is if this is larger than 1? Can we get a negative Q hat? But then we were studying this correction. We were studying this correction, and then you see that actually this thing always has to be smaller than 1, because when this thing becomes larger than 1, the gradient expansion breaks.
Okay.
So the formula doesn't work. And if we then try to assume, okay, let's assume only the density enters linearly in all this business, so it's a very nice object, very easy. So then we thought, okay, let's assume that only the density has this dependence on x, but we do not expand in gradients. We try to keep everything there. So if you do that, you see that you roughly get something that looks like this. And this is basically telling you that the density changes when the medium is moving in front of you. If the density changes in the transverse plane, you are seeing this change. So when you expand this to first order gradients, you actually recover exactly what we get by expanding at the very beginning, from the beginning. The thing is that you don't not only have this gradient of rho, but you also have gradients of mu or whatever. But actually this here would be this G hat that I had before. And this explains the minus sign. So you are seeing the matter that is, if the flow is going to the right, you're seeing the matter to the left.
So in your formula, with or without flow dependent Q hat, the RA will be same.
What, sorry?
I mean, in this formula, with or without flow dependent Q hat,
Yeah.
the RA should be the same.
This one. You are talking about this one?
Yeah.
Yeah.
I mean, if you calculate IA or RPA, nuclear modification factor, with or without flow dependent Q hat,
Yeah.
they are the same. They should be the same. Because
It's pretty insensitive.
right.
Yeah. So
But still, I mean, the flow, we HIPG flow, RPA puzzle still cannot be solved. I mean, in PLAT, still cannot.
No, but what I said about the RAA and V2 is not that because Q hat gets this correction, now the radiation is different. I actually computed the radiation, and I see that the radiation rate gets modified by this. The modification will matter because you are actually modifying the radiation rate, and the radiation rate controls the energy loss, of course. It's just the integral. So it's slightly different. It's not that I found a different Q hat and then I plug the different Q hat and I see what happens to the radiation. I actually computed the radiation and I see that the modification looks exactly the same as the one in Q hat, which in principle wouldn't need to be the same. I mean, it's nice to have the same Q hat that you see in broadening is the one that then is in radiation, but in principle, these are two different processes, right?
Yeah, but if Q hat is a feature of the medium, then they better be the same.
Yes, but
right? You can't find a different medium by scattering off of it than by inducing radiation.
Yeah, that's true, but that just means that the way that we talk about these medium properties, like Q hat, is not exactly the combination that enters in radiation and in broadening, for example. So the medium is the same, but then this Q hat is some integral with some Debye mass, some L and whatever, and maybe the combination is not the same. These medium properties do not affect the same way of radiation and broadening, which I'm not saying is the case.
I think it has to, right? Because the broadening comes from multiple scattering. Right?
Yes.
And so there it's, do you find a parton in the medium to scatter from?
Yeah.
And the induced radiation also comes from the scattering.
Yeah.
So it has to depend on the density and the dynamics of the scatterers.
Yeah, it has to.
So then it should be the same.
It should depend on the same medium properties, but it doesn't mean that Q hat, which is the parameter that we use to take into account this medium property, is going to look the same.
I mean, because the PT transfer doesn't have to be the same.
For example, or many other things. Yeah.
Well, I'm much more, I will sleep better tonight knowing that Q hat still is a medium property.
Yeah,
That the way I measure it doesn't matter, it's still a property of the
But
medium.
here's the problem.
yeah.
I mean, if this is correct, then this depends on flowing medium has a different Q hat than a static medium.
Well, that could be true.
Yeah, well, I mean,
That would
but
make sense, but it has to be the same Q hat whether you are looking at multiple scattering or whether you're looking at induced radiation.
oh, that I don't know. I mean, there's all
Because
these
it comes from the scattering probability, right? Which means your probability of finding a scattering center.
Yeah, but in this case, the flow, I mean, there was too much information in 1 hour, right? But the radiation and the broadening, they are different formulas, and it's not clear to me from all these formulas that I'm always getting the same quote unquote Q hat. Right? Am I? Are you saying that?
Yeah,
No.
that's what he said.
No. Actually, in my radiation, we are doing first order in opacity, so the notion of Q hat is not even there.
Okay. So it's
So you
what
can't
people
answer.
usually call Q hat is not even there.
I see, so you can't answer.
Right.
But theoretically, so what you do is that when you have these multiple scatterings, that you have to take the harmonic approximation. And this harmonic approximation tells you that the potential that controls the interaction can be written in configuration space as Q hat times the difference of where you're scattered in amplitude and conjugated amplitude. And this Q hat you introduce there in the potential when doing multiple scattering. But when doing all this calculation, Q hat is made of the properties of the medium, but it's not one of the variables of the medium. The variables are the density, the length, the velocity. So that is what I mean. But I'm not saying it's going to be different. I'm saying that I could imagine a scenario where it could be different, but I hope it's not.
More questions? Okay, maybe if no more questions, next speaker here.